where we have the opponent, Professor Francesco Iannuzzo from Politecnico di Torino, from Torino, Italy. Professor Iannuzzo will be discussing the thesis together with Bhanu, finding all the stronger and weaker points. I guess, again, for 45, 60 minutes, something like that, so that we really get to know that Bhanu knows what he's been working with. Once the discussion is concluded, we will be moving over into the grading board, who are the powerful people here today that will be assessing the work, and at the end of today, judging whether it's a pass or fail. In our grading board, we are really happy to have Dr. Ivana Kovacevic from ETH Zürich in Switzerland. We have Professor Jacek Rabkowski from Warsaw University of Technology, Warsaw. And finally, we have also Professor Thorbjörn Thiringer from Chalmers, Gothenburg. Very grateful to all three of you for coming to participate in this defense. The grading board members will also be asking some questions to perhaps add on to what has been discussed, or if there's some items that were not covered during the discussion with the opponent. After that, the grading board is satisfied. We will open up for open questions from the general audience, both online and here in the room. If you have a question online, you raise your hand, and we will then enable your microphone so that you can ask the question. Once that's over, the open part of this defense is over, and the grading board, together with opponent, will go to another room to have discussions on what they've heard, read, and seen today. But before starting, I also need to introduce some additional important actors, being the supervisors of the work. So we have Associate Professor Staffan Norrga, who's been the main supervisor. We also have Professor Hans-Peter Nee, who's been a co-supervisor. And finally, also Professor Patrick Hilber, who's been a third supervisor. With that said, I believe I have introduced everyone important in the room, and the procedure can now start. So I will ask you then first, Bhanu, is there any errata in the thesis that you would like to share?
Yes. So in the thesis, in figure 5.5, the term von Mises has been misspelled. The V here should be small because the term comes after the name Richard von Mises. And in figure 8.9.c, the figure states DUT2, but it actually corresponds to DUT3. So there are these two erratas in the thesis.
Okay, thanks very much.
Is it okay now? Okay.
Much better. Yeah. Okay, well, please then, Bhanu, take us through this work.
Thank you, Lars, for the introduction. Dear opponent, dear members of the grading committee, dear audience present here attending this presentation in person, and also dear audience attending the presentation online. Very welcome to my presentation titled Reliability Assessment and Health Diagnostic Methods for Silicon Carbide MOSFET Devices. Let's directly jump to the forecast. So the International Energy Agency published a report in 2025 where they said that in 2024, around 20% of the cars sold worldwide were electric. This includes both plug-in electric vehicles and battery electric vehicles. On top of that, the sales of electric trucks and electric buses also increased by 80%. Here we look at the picture of the power system of the electric vehicle. So basically, the electric vehicle comprises of an electric powertrain and various other energy conversion units. And inside these energy conversion units, we also have semiconductor devices. According to this study released in 2021, they say that approximately 8 to 20% cost of battery electric vehicle is taken by the electric powertrain. And out of that 8 to 20%, 45% is taken by the inverter itself. Therefore, with the electrification, the demand for electric energy converters as well as semiconductor is also projected to increase. We see that silicon carbide MOSFETs are becoming a favorable technology and they are becoming popular, at least in EV applications. And that's because they provide few advantages over silicon devices. For example, they have better thermal conductivity, they have higher melting point, higher energy band gap, and also high critical electric field. In 2022, McKinsey released a report projecting the growth of silicon carbide market, and they said that it will grow by CAGR of 26% per annum. So with adopting new technology, it's also quite important that we understand it from the reliability perspective. In 2011, an industrial survey was done, and they found out that in power electronic converters is basically the power semiconductor devices that are most prone to failure. Even though we feel like this study is quite old, but I think like today also it holds true. In another study, they identified that the primary cause for these failures is the temperature, both in the steady state form and in the form of temperature cycling. Here we are looking at the picture of the temperature inside the power module. And then we see that the temperature inside the power module in electric vehicle cycles, both at low frequency, and if we zoom in, then we see also the high frequency temperature cycling. Coming to the root cause of these thermomechanical failures that I have investigated. Here we are looking at the picture or the cartoon diagram that I made of the power semiconductor module. We see that the power module is made of different materials. For example, in this case, we see aluminum bond wires, and then we have a silicon carbide MOSFET that is soldered on top of a DBC. DBC has a ceramic with copper metallization on both sides. And that DBC is again soldered to the base plate, which is again made of copper. If you look into this picture, then we see that coefficient of thermal expansion of these materials is different. For example, silicon carbide is 3.4 and aluminum is 23. So this introduced the coefficient of thermal expansion mismatch. And also the Young's modulus is different. In general, I would like to say that the thermal and the mechanical properties of these devices are different. So during operation, the temperature inside the device is cycled because of the power losses, which eventually results in the thermal expansion and contraction of these materials. Since they have different coefficient of thermal expansion, this material will expand and contract at different rate. This eventually results in interfacial fatigue, which generates crack. And because of the crack, the delamination occurs, which eventually results in the semiconductor device failure. Here is one picture of the device that we failed in KTH. It might not be clearly visible, but there is a crack at the interface of the bond wire on both sides. Therefore, this device failed at the end of the test due to bond wire liftoff. Coming to the motivation, so we were motivated to evaluate the thermomechanical performance of semiconductor devices, as well as develop the health diagnostic methods to detect package-related degradation. So we had two objectives in this thesis. The first objective was to do the thermomechanical analysis of conventional and advanced silicon carbide MOSFET packages. This eventually resulted in two contributions, and in those two contributions, we generated three publications. In objective 2, we wanted to develop health diagnostic methods using the lifetime data that we gathered by degrading the TO247 packaged silicon carbide MOSFET devices. Under this objective, we had 3 contributions, which eventually resulted in 5 publications. Now I will go through each of these contributions one by one, and I will present the results. Coming to contribution 1 under objective 1. Here, we will look at the thermomechanical performance of single-sided cooled packages. In part 1 of this contribution, we will look at the solder layer reliability. We are again looking at the picture of a power module, and we see here that there are multiple dies connected inside these power modules. So a power module can have many dies inside it, and these dies can have locations, different locations. So we see that the reliability of the solder layer, which is present in the die attach and the base plate attach layer, can vary depending on the location and also the number of dies we have in the module. We did the simulation study using finite element modeling, and we divided the study into 3 packaging configurations: the symmetric, where the die was located at the center of the package; asymmetric, where the die was located in the corner; and then full power module, where we had 3 dies connected in parallel. So first, we will look at the thermal performance of the solder layers. The thermal performance was done using power cycling test, PCT-SEC and PCT-mean. According to the ECPE EQG 324 standard, they divide the power cycling into 2 different categories: PCT-SEC, meaning the heating time is less than 5 seconds, and PCT-mean, meaning the heating time is more than 15 seconds. So PCT-SEC can also be said as a fast power cycling test, and PCT-mean can also be termed as a slow power cycling test. We ensured that the temperature cycling inside the module or the junction temperature inside the module remains same across all the cases. Therefore, we adjust the heat losses accordingly. Another thing to note here is that the base plate attached solder layer temperature cycling is different during PCT-SEC and PCT-min. In PCT-min, the base plate attached solder layer exhibits higher temperature cycling. Looking at the temperature distribution in the die-attached solder layer. Here we are looking at during PCT-SEC. We see that depending on the location of the die inside the package, the temperature distribution also varies. For example, in symmetric condition, the high temperature region is presented towards the central region. This represents the center part. However, in asymmetric, the high temperature region moves more towards the corner. And then the same happens in the full module. Due to the thermal coupling effect, the temperature in the full module is also impacted by the second die, which is connected in parallel. When we look at the temperature profile that is plotted across this diagonal, we see that during PCT-SEC, the high temperature gradient is observed. However, during PCT-min, this temperature gradient reduces. Another important thing to note is that in asymmetric and full module case, that the region which is closer to the DBC corner and edges have higher temperature than in the other end. Now looking at the thermal performance of base plate attached solder layer, this is analyzed during PCT-min. And we see that depending on the location of the die inside the package, the temperature distribution inside the base plate attached layer also changes. For example, in symmetric, we have the high temperature region in the center. However, in asymmetric case, the high temperature region moves towards the corner or the edge. Additionally, the presence of more die introduces more high temperature region, I will say. Now coming to the mechanical performance. First, we will go through the die-attached solder layer. For the solder layers, we used accumulated viscoplastic strain as a performance criteria. Here, we are looking at the viscoplastic strain accumulation in the die-attached solder layer calculated during PCT-SEC, one cycle PCT-SEC. In symmetric condition, the viscoplastic strain accumulation was a bit lower. However, in asymmetric condition, the strain accumulation increases. And we see, if you look at this edge region, then we see that this area experiences very high viscoplastic strain accumulation. The same observations were made in full module. One important thing to note here is that this area, which is also closer to this parallel die, also exhibited a bit high viscoplastic strain accumulation. So we see that the location of the die and the number of dies that are connected in parallel have an impact on the viscoplastic strain accumulation. If we compare it with the strain accumulation during PCT-min, then we observe that during PCT-min, the strain accumulation was a bit more uniform around the edges, as we see in the asymmetric and the full module condition. Now I will go through the mechanical performance of the base plate attached solder layer. Again, here we use accumulated viscoplastic strain as a performance criteria. And this was done during PCT-min power cycling. So in the symmetric and the asymmetric case, we observed that it's mostly the corner regions which exhibits higher viscoplastic strain accumulation. We didn't see much difference in between symmetric and the asymmetric case, but in the full module, we see that a big portion of the edge experienced higher viscoplastic strain accumulation. We also did a lifetime estimation study using Morrow's energy-based lifetime model. Here, we used viscoplastic dissipation energy density in the die-attached layer to calculate the lifetime of the die-attach. We see here the viscoplastic dissipation density during PCT-SEC and PCT-min. And here we can see that depending on the configuration we have, the dissipation energy density also changes. We feed this dissipation energy density in Morrow's energy-based lifetime model, and then the software gives the lifetime distribution in the die-attached solder layer. We see that in the symmetric condition, in all the cases, we see that the solder material experiences lower number of cycles to failure around the edges, like here and then here, which is represented by red and dark red color. We see that the symmetric power module exhibit higher number of cycles to failure in comparison to the asymmetric and the full module. And in these regions, they have like the minimum number of cycles to failure. Plus, in this region, in the full module, the number of cycles to failure also reduced because of the presence of parallel die. If we look at during the PCT mean, then the lower number of cycles to failure distribution is uniformly distributed around the edges. So from this study, we concluded that the location of the die inside the package and also depending on the number of dies we have in parallel, the reliability of the solder material we used inside the package varies. Coming to part 2 of this contribution, here we analyzed single-sided cooled packages, advanced packages. So this study was divided into 4 packages, aluminum, the one with aluminum bond wire, second with copper bond wire, third with sintered copper clip, and fourth with sintered copper foil, having aluminum bond wire on top. In order to make this analysis simpler, we divided these packages into 6 cases. It's also important to note that in the die attached layer and in the base plate attached layer, we are also investigating solder and silver sinter in order to do the comparative analysis. Now coming to the thermal performance of these packages. This was evaluated under steady state condition. In this figure, we are looking at the power losses that the module were able to handle for the same steady state junction temperature. If we focus in the first 3 cases, we see that we have say aluminum bond wire on top, but the die attach and the base plate attached material is changing. And we observed that by replacing solder material with silver sinter, we have better thermal performance. If we also focus on the on case E and case F, then we see that introducing copper clip on top or copper foil also improves the thermal performance a bit. In this figure, we are looking at the vertical temperature profile through the die center in case A, B, and C. And we see that in case of that the temperature drop across the solder represented by this blue curve here and here is higher than in silver sinter. And that's because solder material has higher thermal resistance than silver sinter. Now, looking at the mechanical performance of these packages. This was evaluated using PCT-SEC power cycling. Here, the cooling time and heating time are set to 2 seconds each. First, we will look at the die attach layer, which involves solder or silver sinter. And again, we use viscoplastic strain accumulation as a performance criteria. Here, we are looking at the accumulated viscoplastic strain during one PCT-SEC cycle. And we see that the die attach solder layer exhibited higher viscoplastic strain accumulation than silver sinter. We also calculate the volume averaged viscoplastic dissipation energy density in die attach layer. And we see that the solder layer, which is represented by this blue curve, exhibited higher viscoplastic dissipation energy density than the silver sinter material, which is shown by these plots here. Therefore, we concluded that the kind of material we have inside the package, the performance will, mechanical performance and thermal performance will change at attach. Now we will go through the mechanical performance of the die top side interconnection. First, we will start with bond wires. So the performance of the bond wires was evaluated using von Mises stress and also accumulated plastic strain. Here, we are looking at the von Mises stress distribution on the surface of the bond wires. We see that aluminum bond wire in case B and copper bond wire in case D have higher higher von Mises stress at their surfaces. However, in case F, it's reduced, and that's because we are using a copper layer in between the die and the copper bond wire. I would also like to mention that these plots were plotted at the maximum junction temperature. Here, we are looking at the accumulated equivalent plastic strain. So this is a bit different. It's not viscoplastic, it's plastic. And we see that the plastic strain accumulation in aluminum bond wire is higher than copper bond wires. And that's because the yield strength of aluminum is lower than the yield strength of copper. In case F, we see that it's minimum. Now, looking at the die top interconnection silver sinter, here we see the viscoplastic strain accumulation in die top silver sinter layers. And if we focus on this region, then we observe that in case of copper clip, the die top silver sinter accumulated a bit higher viscoplastic strain than what we used in case of copper foil. Looking at the average, volume averaged viscoplastic dissipation energy density, then we see that it is a bit higher in case E with copper clip than case F with copper foil. So from this study, we concluded that the kind of material we are using inside the package and also on the kind of configurations that we have in the module, the thermal and the mechanical performance both can vary. Coming to the coming to contribution 2 of objective 1, here we analyze the thermomechanical performance of double-sided cooled packages. The double-sided cooled packages are becoming quite famous now because they allow for higher heat dissipation from both sides, from top and the bottom side. However, in order to create some space inside the package, which facilitates connecting the gate terminals, we introduce a spacer inside. And we were interested in studying the impact of the spacer material on the reliability of the solder layers. We used spacer materials that were composed of different percentages of copper and molybdenum. And depending on the percentage of copper material we have inside the spacer, this number varies. So basically, 60 here represents it's 60% copper. Since copper has 3 times higher coefficient of thermal expansion than molybdenum and 3 times higher thermal conductivity than molybdenum, so the thermal and the mechanical properties of these spacer materials will also vary with the percentage of copper and molybdenum inside them. Starting with the thermal performance of these packages, this was again evaluated at steady state. Again, here we are looking at the power loss that these packages were able to handle for the same junction temperature. So we see that double-sided cooled packages, which are represented by these bar plots, have higher power loss handling capability than single-sided cooled packages. Also, the power loss handling capability increased with increase in copper percentage in the spacer material. Again, looking at the vertical temperature profile through the Ag-sinter, we see that molybdenum exhibited higher temperature drop across it than copper. And that's again because molybdenum has 3 times higher thermal resistance than copper. Coming to the mechanical performance of these packages, first we will start with silicon carbide die. This was evaluated using steady state analysis, and we used von Mises stress as a performance criteria. So what we see here is von Mises stress on top surface of the die, and we observed that von Mises stress is higher when the copper percentage in the spacer composite is also higher, and it reduces with decrease in percentage of copper. Therefore, in case of molybdenum, we see minimum von Mises stress on the die. The performance of the solder layers was evaluated using PCT-SAC and PCT-min power cycling conditions, ensuring that the junction temperature profile is the same in all the cases. In this case, we took a different approach. We basically used the 10% delamination criteria. In this figure, you are looking at the viscoplastic dissipation energy density distribution around the edge. And we see it's uniformly distributed. So we have a quarter symmetric in this case. We use line 1 in this case to calculate the viscoplastic dissipation energy density. And based on 10% delamination criteria, we calculated this length, and we call it crack length, and it is 0.13 mm. And then this viscoplastic dissipation energy density in this crack was fed into this formula to calculate the line averaged viscoplastic dissipation energy density. Here we are looking at the viscoplastic dissipation energy density along line 1, which is basically this line. And we see that in the central region, the dissipation density is a bit lower, but it increases drastically towards the edge. Therefore, we use the dissipation density in this region, in this formula, to calculate the line average viscoplastic dissipation density. And then here we plot the line average viscoplastic dissipation energy density in different layers for both PCT-SAC and PCT-min. There are a few trends which we can see here. First, that DA bottom solder layer, which is underneath the die, exhibited the highest dissipation density, both during PCT-SAC and PCT-min. And this dissipation density also increases with increase in percentage of molybdenum. However, in DA top solder layer, the trend reverses. So the dissipation energy density reduces with increase in percentage of molybdenum. In the spacer attached layer, we didn't see any specific trend. In PCT-SAC, we see that it first decreases and then increases. However, in PCT-min, we see that it increases. Therefore, from the study, we concluded that depending on the kind of spacer material we are using inside the double-sided cooled packages, the thermal and the mechanical performance both can change. Therefore, it's important to optimize the package depending on the operation. Now we will look at objective 2, where we basically developed health diagnostic methods for detecting package-related failures. Looking at the contribution 1, we basically here developed the degradation experiments to collect the lifetime data by degrading TO247 packages. We started building the test bench. First, we started with inverse mode power cycling test. In the inverse mode power cycling test, body diode is used for generating heat, and the DUT, the device under test, which is basically silicon carbide MOSFET, is always kept in an off state in order to ensure that the MOS channel is completely off. The heating current source is turned on and off for providing the heating and then cooling. Here we have a measurement current source, which is always kept in an on state. We used 10 amps of heating current and 10 milliamps of measurement current. The control strategy that we used in this test was constant junction temperature swing, that is constant delta T. Here we are looking at the temperature cycling profile. We see that during heating, the temperature rises, and during cooling, the temperature dropped. So it's basically the difference between Tj max and Tj min, which was kept constant. The temperature measurement was done at the middle leg of TO247 package with the help of K-type thermocouple. And that's done because the middle leg or the drain leg is directly connected to the copper lead on top of which the silicon carbide die is soldered. So this provides a better access, I will say, or easier access. We also measured body diode forward voltage at 2 points. First is at the maximum junction temperature. This is measured with the help of heating current, that is 10 amps. And second, at the minimum junction temperature, which is measured with the help of measurement current, that is 10 milliamps. We tested the devices from ST Microelectronics. Here is the model number. This device has only single bond wire inside it. This is the gate bond wire, but what we are interested is in the source bond wire, which is this one. Looking at the results, first we are looking at the body diode forward voltage measurement done using 10 amps current. So we see that it remained constant until this voltage increased drastically towards the end, where we concluded that the device has failed. We also observed the voltage measurement at 10 milliamps current. One important thing that we notice here is that the voltage remained same even after the device has failed. However, after a few hundred cycles, this voltage starts dropping. We did some output characteristics test. Here we see that the on-state resistance increases with cycling. And in this cycle number, which is 4756, this measurement is done after the device has failed. And we see that it showed a very high RDS on. And then at the end of the test, when we have also observed this reduction in this voltage drop at low current, we see that RDS on has become quite high. So we were interested to see like what happened here. So we also measured the gate to source resistances, and we observed that at the end of the test, the gate to source resistance changed from open to 603 ohm. So we estimated that the device has failed because of shortening of gate and source terminals. Okay. After inverse mode power cycling test, we proceeded forward with building a forward mode power cycling test. Here is the overall layout of the test bench that we created in KTH. We can see a PCT circuit diagram here, and then a heating current source, the data logger that we used to collect the degradation data, and the workstation to display the parameters online. Focusing on the circuit diagram, we see that the DUTs, the devices under test, were connected in series, and each DUT has its gate driver. Using this gate driver, we were turning on and turning off the DUTs. We were also able to adjust the losses inside the devices by adjusting the voltage out of the gate driver. For the temperature measurement, we used a temperature-sensitive electrical parameter, body diode forward voltage, which is measured at 100 milliamps measurement current. Here, we are looking at the calibration data of this TSEP. So we see that the body diode forward voltage changes with junction temperature. We feed this calibrated equation directly into the test bench, and during the cooling time, this gives us the junction temperature. We tested two different kinds of devices using this test. First one is from ST Microelectronics with single bond wire, and the second one from Cree, which has 4 bond wires connected in parallel. This is how the DUTs were mounted. So we had a air-cooled heatsink for each DUT, and then the DUTs were mounted on these heatsinks with the help of clip. We have a thermal interface material in between the heatsink and the DUT. During the test, we also measured the temperature of the middle lag with the help of K-type thermocouple. So here we are looking at the measurements during the forward mode power cycling test. We see that during the cooling time, that is T off, the temperature dropped, and during heating time, that is T on, it represents the on-state voltage. The red curve here represents the temperature measurement done at the middle lag with the help of thermocouple. So we see that the temperature increased during the heating time and then drops during the cooling time. Here we are looking at the scanning acoustic microscopy images of 2 of the degraded devices. The SCT in the device terminology basically represents the DUT name, and the numbers here, represents the DUT number. We tested around 8 to 90 devices. That's why, and we used this 19 and 55 from the test database. The red region here represents the delaminated area. We should focus more towards the die, which is represented in this region. So in SCT19, we don't see any delamination. However, in SCT55, partial delamination at the edges is observed. We also did the cross-sectioning and then took the scanning electron microscopy images. In both the devices, cracks were observed at the interface of the bond wire. Therefore, these packages have mainly failed because of bond wire failure. So we used their test results to develop health monitoring techniques by compensating on-state resistance. So the on-state resistance, here in this contribution, we used this device with single bond wire, the SCT30 and 120 from ST Microelectronics. So the on-state resistance can be decomposed into several resistive components, like shown here. If you look more towards the die, then it can further be decomposed into channel resistance, drift region resistance, and substrate resistance. In literature, they say that it's mostly the channel and the drift region resistance which contributes the most towards our die. So here we have the equation of the channel resistance and drift region resistance. If you look at the channel resistance, then we see that it also depends on gate to source voltage and threshold voltage. It's important to note that the threshold voltage drifts during power cycling because of bias temperature instability, which also eventually results in R channel and RDS on drift, which we will observe later as well. So first, we started with the temperature compensation method in order to remove any temperature-related effects from this parameter. Here, we are looking at the readings that were taken from the power cycling experiment. We are looking at the RDS on that is measured at the maximum junction temperature. So the red curve here represents the maximum junction temperature, which is also termed as TJ max. And the blue curve here represents the maximum on-state resistance, or the on-state resistance at the maximum junction temperature, which is also termed as RDS on max. And we use 2 devices, SCT55 and SCT19. If we focus in this highlighted region, so we use the TJ max and RDS on max data from this highlighted region, and then we plotted RDS on max with respect to TJ max. One important thing to note here is that SCT19, RDS on max in SCT19 exhibited positive temperature coefficient, while that in SCT55 exhibited negative temperature coefficient. So using these samples, we came out with, we derived the second order polynomial fit function. And then by feeding the maximum junction temperature, TG max, in this second order polynomial fit function, we calculate the expected value of RDS on max, which is represented by red curve here. The blue curve represents the measured value of RDS on max. And we see that the 2 curves diverges from each other, and the rate of divergence increases towards the end of life. Similar observations were also made in SCT55 device. Then we used the RDS on max and R hat D on max, which is the expected value, in the temperature compensation model, which is represented by these equations. Here, delta RDS on max represents the temperature compensated parameter. So after feeding these signals into this compensation method, we get this output delta RDS on max. That is the temperature compensated on-state resistance. There are a few important things to note here. The first one is that the signal showed a linear drift initially, like here and also here. However, towards the end, the drift becomes exponential, like here and here. So we divided this into two different phases, the NLD phase, which is also termed as near linear degradation phase, and EOL phase, which is also termed as end of life phase. What we wanted to do is that we want to compensate this linear increase due to drift in NLD phase, and then we wanted to see when the EOL phase starts occurring. So for this, we came out with the drift compensation method. First, we will go with method 1. So it's pretty simple. We basically calculate the slope of the signal in order to compensate it. So here we do numerical derivative, and then after that we use moving average filter. So the temperature compensated signal was fed into the numerical derivative function, and then we see a signal which is full of noise because the derivative also amplifies the noise. Therefore, we applied a moving average filter. And we see that the filtered outputs can clearly distinguish in between the NLD phase and the EOL phase. We also developed a second method which used recursive least squares estimator. So here we fed the temperature compensated signal into the RLS estimator, and it directly gives the slope estimates. One important thing to note in the recursive least square estimator is the term lambda, which is called forgetting factor. So the value of lambda is selected depending on how fast your signal is changing. If the signal is changing fast, then it should be lower. But in our case, we have a slow increase in the beginning and then a very fast increase in the end. Therefore, we check this for different values of lambda. And we see that at lambda 0.5, the noise is still quite high. However, it reduces with 0.995. So we see that lambda is equals to 0.995 provide better output. However, it's also important to note that with increasing lambda, there are also delays. So from this, in this contribution, we were able to finally develop a method which can be detected which can be used to detect package-related failures in TO247 package. We used the same method in the device with multiple bond wires and developed a method, we proposed that this can also be used for detecting bond wire lift-off events in the package. So here we use the data which from degrading this Wolfspeed devices which has multiple bond wires. The process is the same. First, we take the RDS on max and TJ max values from the power cycling test. Here we use 3 devices. In the highlighted circle region, we see that the RDS on max is increasing in steps, and each step basically represents bond wire liftoff event. So we took the data from the initial highlighted region to calculate the second order polynomial fit. And by using the second order polynomial fit and the RDS on max in the temperature compensation model, we get delta RDS on max. That is the temperature compensated signal. And and here again, you can see that there is a drift here, and then there's a jump. So this jump corresponds to bond wire liftoff, and the drift is because of threshold voltage. So when we feed this temperature compensated signal in the RLS estimator, we get the output like this. Here, the drifts has been compensated, and we have peaks. So what we see here that these peaks correspond to bond wire liftoff events. So these peaks can basically help us in detecting the bond wire liftoff events, at least during power cycling. In summary, the thermomechanical analysis of conventional single-sided cooled and advanced single-sided cooled, as well as double-sided cooled packages was performed. So we studied the die placement, the interconnection technologies, and the packaging configurations impact on the thermal and mechanical performance of semiconductor package. We also see that advanced packaging solutions provide better thermal and mechanical performance in comparison to conventional packages. In the second part of this study, we developed health diagnostic methods using compensated on-state resistance. And we use this method to detect package-related failures and also detect bond wire liftoff events. Yeah. Thank you for attending the presentation. That's all. Thank you.
Thank you very much, Bhanu. Let's have a 4-minute leg stretcher, and we start again at 10:45. Okay. Yeah. It was intense, yes. Yeah, exactly. So do you want to come up here and we can check if your slides are, because you want to do the slides right away, isn't it? Yep. Bhanu, can you help find the Francesco slides?
It might be. So fast. So here. Yes. You can go for it.
So what I'll do, introduce that there's no discussion, and then say that we use these slides as well.
Yes, please. Just if I may. Just because I'm getting so I could what what's this? Allow me. So it's going to be yeah. I just yeah, please.
Yes.
Oh, I can use the ice cream mic.
Yeah, but perhaps there is whatever you choose. Or actually, if you're sitting down, there's those mic.
No, I can't.
You prefer to stay in here? Okay.
Pointer.
Of course, yeah. Okay, yeah.
One, two, three. It's muted, right?
No.
1, 2, 3. I'm not sure. Can you?
Let's see if we can.
One, two, three. Is there any microphone number here? Number 2.
So
You can hear it. Okay. Can I bend it? Oh yes. Oh yes. Yes. Oh, you're right. I can.
Yeah.
That's it.
I see. Ja, ljudet var lite svagt. Fast när man kan. Finns det någonstans man kan skruva upp? No. Just really short.
Okay, please take your seats. Glad to see you back in the room, Bhanu. You're important. Yes, thanks. So we're ready to continue the defense, and there will be now a discussion between Bhanu and Francesco, and I think you will be starting by giving an overview presentation before we get into the discussion.
Yes, please.
Please.
Yeah, thank you for having me here. Thank you in particular to Staffan. The idea behind making a slide deck was inspired by another defense in Sweden, in Lund University, where there was an excellent opponent bringing up some slides. And then I decided, okay, I will try myself. So today I will present a slide deck which will help me opposing your PhD. So first of all, thank you for having me here. I'm Professor Francesco Iannuzzo from Politecnico Torino, Italy. And I'm here for assessing the PhD dissertation of Bhanu, as everyone know, titled Reliability Assessment, Health and Diagnostic Methods for Silicon Carbide Power MOSFETs. I organized my opposition in 4 parts. Basically, the first 2 are the most important ones. The last 2 are absolutely minimal. I would say a couple of slides in total, so that's it. It's going to be taking in total 7 hours, 25 minutes. Of course, I'm just kidding. So no worries. I will try to stick into the 45, 60 minutes allotted for this opposition. So let's start with goals and methodology, just to make sure we're on the same page. I correctly got what you did. So 9 chapters, dissertation, 70 pages, plus bibliography, not bad, I would say. You can see the page distribution. This is a typical form of PhD thesis called the collection of papers, which I love, basically because you can reuse profitably the work you did during the PhD course in terms of publication, to put them together and giving them a common frame, which I love. Structure is prior art, analysis, development, and conclusion, with, I would say, a nice balance among these things. We will be digging into details more. A few words about bibliography. I won't touch bibliography any longer, apart from this slide. 63 references, not bad, I would say, and 40% of which, 25 in number, in the last 5 years, so rather, I would say, updated bibliography. The oldest paper you had cited is back in 2021, but for a good reason. It's the Anand viscoplasticity paper. So it's a Bible, I would say, paper. So perfect. That's great. Let's move to the scientific outcome. You published 1 journal publication plus 2 submitted. I have a little bit of comment here. It's a little bit close to the limit. I would have expected a little bit more in terms of, so to say, productivity. However, you have you scored 5 conference publications, right? And 5 more conference publications, which for some reason are not included in this PhD thesis. 2 of which are actually relevant to your topic. One is reliability study on SiC MOSFETs following partial failure, and the other one was on line condition monitoring, and the other 3 being a little bit further from it. So fine, I would say. I couldn't evaluate these 2 by no means, simply because you didn't include them. I was in principle not allowed to look outside, the borders. Let's move to the purpose of your thesis. So you want to, by the way, at the time I wrote this, I prepared this slide deck, I didn't attend your presentation. So every single consideration from this slide deck is coming from your dissertation and nothing else. According to section 1.2, investigate thermo-mechanical performance. We saw an interesting presentation on your side. Understanding their failure mechanisms, examine advanced packaging materials to improve performance, absolutely. Design a robust power cycling setup. Here I will share some comments to you. And use power cycling data for development of reliable health diagnostic method. Interesting, and I would say catchy. So, original contributions, again, according to section 1.5, thermo-mechanical reliability analysis of silicon carbide MOSFET packaging, topside interconnection evaluation, basically bond wires. Which kind of bond wire? Aluminum bond wire, copper bond wire on aluminum, copper bond wire on copper, DBC style. Danfoss bond buffer style, DBB style, or ribbon. So yes, bottom side, solder, sinter, something like that. Power cycling, setup and results, health diagnostic condition monitoring method, and development of detection method. You called it early, but I have some comments over there. So let's stick to detection method for the time being, for bond wire liftoff. And I don't want to go through it, but for each of them, you duly corroborated your statements with the publication. So we'll be also going through them in a while. Which approach did you use? You used a simulation and analysis, used extensive, I would say, use of finite element simulations based on COMSOL, if I didn't
COMSOL
catch
Multiphysics.
COMSOL Multiphysics. When I say multiphysics is basically thermo-mechanical analysis, right?
Yes.
Not much electrical analysis.
No.
Although in chapter 2 you were tempting me with your electrical model. Actually, you didn't really use it in your simulation. You started from thermal part and then you moved all the way down to the mechanical part, which is fine. Material and geometries were given, to my best understanding from previous works, is not your direct measurement on the die, on the, you didn't make material inspection. No. You just found on the database, which is also absolutely fine. And the aim was investigating alternatives to wire bonding and solder, investigated thermomechanical performance, so which degrades first and why. We discovered that in the corner is worse than being in the center and something like that. Yeah. You developed a power cycling tester. You have a couple of questions over there in a while, aimed at collecting original data to instruct the L monitoring method. However, even before we start, I was puzzled by this choice. So why, and this is my first question actually, why not TO-2474? I would say no crazy designer nowadays would go for TO-247, standard 3 lead packaging. Not even for a, Wolfspeed is in trouble, we know, we are all cheering for them, that's not the point of this dissertation, of this defense, but why using generation 2? We have generation 3 at our disposal. So can you elaborate a little bit on this?
Yeah, so basically we were looking for the package which has multiple bond wires, and it was we found this one in one of the research, and it was also available to buy. So without investigating if it's generation 2 or generation 3, we directly go with that, because this algorithm by compensating on-state resistance, we had already developed or worked on it using these ones from ST Microelectronics. And there is also a reason why we used ST Microelectronics package.
And that was 3 leads package.
I'm sorry?
And that one was 3 leads package.
3 leads, yes. So it's because the research was already being conducted in RISE on these packages, and we already know that it has one bond.
Sounds like it's your supervisor's fault. Whoops. All right, fair enough. It's an explanation. I mean, it's a little bit of a pity because your results are sound, are interesting. However, they apply to a generation 2 device or 3 leads device. So when I go designing with my 4 leads, silicon carbide MOSFET, I say, may I really apply these results to my case or not?
Yeah.
So it's more how beneficial your results are to the community rather than, being scientifically sound or not. All right. Okay. Thank you. Once this one has been said, I think we are on the same page. I think what I mentioned is actually, somehow matching what your PhD thesis was. So let's go to comments and remark, which is obviously the biggest part of the story, right? So chapters and publications, obviously, because this is a collection of paper. Let's start from minimal things. Reference 2 is appropriate. So I was reading and actually was thrilled by your introduction because you did a great job also in the introductory part. However, I have the bad habit, to say, stopping to the reference and going to page 74 and check the reference. And then reference number 2, Gupta and Majumdar, reactive power compensation in a single stage differential mode solid state transformer. When we talk about the application of, energy transition and, I would say it's not appropriate. I would say in that respect, I would have used a more general, review paper talking about transition, talking about efficiency, and not really about an algorithm, right? A compensation of reactive power, right?
Yeah.
So please pay attention in the future.
Yeah,
I mean, it's nothing major, definitely not, but please pay attention. Be a little bit, control freak when it comes to referencing things. And reference 4, basically the same. You mentioned this inverters and DC. Can you see the pointer, by the way?
Yeah.
Yes. Inverters and DC-DC converters, and then a novel modulation scheme for isolated PWM. Again, we're in the general part, EV comprised electrical power trains, and then you cite something which is algorithm level, right?
I understand.
Pay more attention.
Yeah.
Yes. All right. And this is probably, again, redirecting a little bit to your supervisors who have been whipping you when you used maybe not the perfect reference in this case. All right. Just kidding. Now, let's go a little bit more into some pillars of your PhD. CTE versus Young's modulus. All the thesis, from the beginning to the end, you have been stating that there is a CTE mismatch, in particular between silicon and silicon carbide, but obviously from semiconductors to copper and the remaining materials in the packaging. However, coefficients of thermal expansion, to me, is something very well known, but speaking about how materials expand during heating, because of heating, right? However, they are constrained in packaging. So silicon cannot really expand, copper cannot really expand. At least they can expand, but under the constraint that they expand together. You cannot have this because you have a crack, you have a delamination. You only have this. So the problem actually causing your foam misses stress and whatever you duly talked about is not about different CTEs. It's about different Young moduluses. Because they are constrained. Strain is constrained. And what you get is actually that because of very different Young's modulus, you have a lot larger force in one material than you had in the other material.
Yeah.
Than in silicon, than in silicon.
Yeah.
In silicon carbide, than in silicon. Can you comment on this?
Yes, I would like to comment on this. So basically, silicon carbide is much tougher because it has a very high Young's modulus.
Yeah.
And it's basically, then we can say, like, we have one soft material and then we have one hard material. So even though the mismatch is not that different, but what happens when the material, like solder layer, stretches because of the thermal expansion, silicon carbide will have higher impact on the solder layer, which will eventually result in much more higher strain accumulation because of very high Young's modulus. In case of silicon, it's a bit softer. So that's why we also observe that if we use the same technology.
But that's because of Young's modulus.
Yeah,
not because
modulus.
of CTE.
Yes, that's why I'm said Young's modulus.
Yes.
I mean, so that's why it's also important to include Young's modulus.
That's exactly my point.
Yeah.
Instead, you mentioned over and over difference in CTE, which actually turn out not to be that different. 3.4 versus 3.
Yeah.
I agree. It's 10% more higher. Look at the Young's modulus. 5 times higher.
5 times high. Yes.
Right? So, minor thing again. But all right. Still introduction, chapter 1. Oh, by the way, this was kind of a praise of mine. Every second PhD defense I attend or I'm opponent about is about artificial intelligence in power electronics. Thank you, actually, not stating that artificial intelligence is essential nowadays to understand power electronics and reliability, right? That's definitely not true. I mean, the artificial intelligence is a key technology, but not in our field, not at the moment, I would say. So thank you very much for this. But this was a little bit for fun. Let's move to chapter 2, which is actually, I would say, the core of your thesis. You made a lot of calculations, which are actually correct. I checked. I agree with each step of your calculation. However, you disappointed me because we ended up in an experimental / I would say empirical relationship, which is true as well, between on-state resistance and gate source voltage. So this is actually measured, right? So you made a lot of mathematics, I mean a lot. You made nice and acceptable level mathematics, but that you end up in a measured something, right? You never use this mathematics any longer. Probably you mentioned it once where you talk about the relationship between the on-state resistance, which is indirectly related to the threshold voltage through the channel resistance, right? And you correctly stated that there is a one-to-one, there is a direct relationship between threshold voltage and the channel and RDS on. But other than this, you're not really using this one. So I was really thrilled and waiting for this fantastic comprehensive mathematical model of crack damage, which I look forward to find very, very much, by the way. And then, okay, measurement. Right.
That I agree. That the thesis and the papers lacked a little bit of mathematical verification.
Right.
We have mostly focused on the experimental data.
Right.
So it has become more kind of a practical application rather than,
Yeah, this was an encouragement actually to if you can take it like this, to believe more in yourself. I mean, there is a lot of things you can do just sticking on models, on mathematics, and prediction based on mathematics cannot be that wrong, right?
Yeah.
So making prediction with models and then validating it with experiments or even with COMSOL simulations would be another level. But making math for its own purpose is probably, not saying waste of time, but maybe, ending right away, right? So, yeah. Still chapter 2. Again, we discussed about this, so I don't want to touch this anymore. Now, in my experience, this is actually quite general, it's not just related to chapter 2. In my experience, using the temperature swings you have been using, no matter PC min or PC sec, I observe, using your numbers, 145 maximum junction temperature, I don't remember what your temperature swing was in the range of 60 Kelvin or whatever. Well, I get in the range of 100,000 cycles to failure.
Yeah.
You have one order of magnitude lesser.
I can comment on that.
Please.
Yes. So basically, as I mentioned, we use this Morov's energy-based lifetime model. The parameters were not experimentally driven. They were taken from the previous study. And these parameters depend on the material type and the material, the dimensions of the material. We ensured that if we had the same material, so the study that we were referring to while doing the simulation, we took the material from there. So basically, regarding the material, that is satisfied, but the dimensions might be different. So that's why I think...
that's one thing for sure, but you have also experiments. And your experiments, you fail actually, your devices, your samples in 25K, 30K cycles.
Yeah, but it's a bit different. The experiments we had in TO247, that one has a lead-based solder. And what we used in the simulations, like when I started my study, I started with the simulation, and the final motivation was to fabricate the package using the materials that we are using in the simulation.
But they're commercial. You didn't fabricate your samples. You tested commercial samples.
TO247 packages, yes. But I will say they don't represent the COMSOL model.
I know, but anyway, you failed in 25K cycles. Why? Yeah. I suspect there was a significant mismatch in your measurement. Your measured temperature or your inferred temperature. We can discuss later when we go to chapter 7. But this was a flag I wanted to raise at this time.
Yeah.
Yeah, viscoplasticity. But then, yeah, exactly. We should be always careful about this because everything you did, in my opinion, applies one-to-one to silicon. We use a solder, sinter, bond wire, copper bond wire, Danfoss bond buffer, also in silicon, for successfully. So whatever you are basically dealing with, probably except for condition monitoring chapter 8, except for that, it's one-to-one applicable to silicon, which is great. So thank you for this. But be careful when you state that it's because of silicon carbide you're making this calculation, because everything is the same, stays the same with the silicon, right?
Okay. Yeah.
So it's unnecessarily limiting your work. This is applicable to IGBTs, to silicon in general. So MOSFETs in silicon, why not? It's not because of silicon carbide. Young modulus or CTEs, yes, that's it. But that's another story. The approach is the same, right? Publication 5 related to chapter 2, I remember here I have a couple of minor comments here. So this is, I don't want to, you know exactly what your publication is about.
Yeah.
It's not a groundbreaking study, definitely. I like the systematic approach. So you took little by little, starting from scratch, and then, yeah, I liked it. Why did you use different heating times constants? This is a key point. Yeah. There is an original, I would say, a background flaw, which is you're not using electro-thermo-mechanical simulation. You're only using thermo-mechanical simulation. So you obviously had to profile your power, your power dissipation into your chip. And then I have a question. Why did you use this low? In particular, this is, yeah, exactly. This is a PCMin.
Yeah.
Why did you use this low? You cannot make this low temperature rise. You cannot make, except for an artifact. I mean, when you go PCMin, you power unpower for a minute or so. And when you power it up, the temperature goes just as steep as in the PCSec case. You know, it takes what it takes. It takes, what is this? Is 1 second?
Yeah, 1 second.
And then what is 1 second in this time scale here? It's a step, 2.
Yeah.
And then what? Please comment.
Okay, so at that time, actually, we were not sure how the actual temperature profile looked like. So we started with the COMSOL simulation, and then the main focus was on to degrading different solder layers. Like in the slow power cycling, we wanted to focus also on the base plate attached layer. So that's why we created this slow power cycling.
This is risky because your simulations and your conclusions based on your simulation might be questionable because of that.
Okay.
And I actually know, I tried because I went to AQG324, which I used very, very much. And I spotted the problem. They put in the PCMin section, they put a chart which with no time scale, just put 1 minute, and they mistakenly shown a
it's like
lower, and then you probably took that one as an example. My rise time is too fast, so I should stick to AQG324. But actually, the wrong one was AQG324. Was not you.
Yeah, we were following this AQG324 a lot, and yeah, we can say.
Be careful.
Yes.
Another thing is minor thing is. You use the symmetry, which obviously in engineering is the basis. So come on, I have a chip in the very middle of a square, in the very middle of a square package and whatever. So why should I simulate 4 times as big my mesh? Just use 1/4. Yes, I agree with you. But when I get the results, how can I compare 1/4 of a chip with a full chip? This is 1/4 of a chip. This is a full chip. They are not even the same geometrical scale. This one compares to this one just as a quarter here. How can I compare this with this? It's totally misleading. So please use symmetry, simplify your work, no question. But then when you present your results, put again everything, the picture together. I mean, the layman can say, oh, okay, I understand. In the case of symmetry, I only have the left-hand side and the bottom side, which are wearing out. In the top one and the right-hand side is not happening nothing, which we know is not true because we're in the middle of the chip here, we're in the middle of the chip here. So this is actually the picture you should compare with. So please remember when you use symmetry, which is also the case here, you use half symmetry in this case, not the quarter like in this case, please reconstruct the picture. So butterfly, and show me the full picture. Then I can compare. And this is actually common throughout your thesis. This mistake has no exception.
Yeah, I understand your point, yes.
Do you see my point?
Yeah, I completely understand your point. It's also very difficult while presenting as well.
Yeah.
When we don't have this.
Again, I don't want to say anything about the publication. You also presented it very well, by the way, during your presentation before. So again, it's not a groundbreaking study, but I like the systematic approach, starting from hypothesis, and like it. Absolutely fair publication. You only used fast power cycling.
Yes.
Which is probably correct because when you talk about bond wires, we know that the PCMin is negligible compared to PCSec, but you should probably you mentioned it, probably. I didn't honestly read every single line of the publication, but yeah, this is as it is. And by the way, the footprint of your bond wire is, I mean, you gave me the impression that the footprint geometry was a little bit of a given. So you took an oval, not really.
Yeah, I mean, in the future, like in the final year, we were also trying to investigate bond wire. At that time, we had different geometry, but this was the first bond wire that I modeled, and
I kind of felt it, but fine, it's fair. Again, as I mentioned before, good. Publication 7, double-side cooling, symmetry, symmetry, symmetry. Remember, same thing here. But my point here was another one. You used both fast and slow, min and sec power cycling, great. But why the temperature rise is so slow, we commented on this, is the same issue, I would say. You assumed heatsink have the same temperatures. Look at this. You made the top and the bottom thermal network here.
yeah,
And then you assumed I have a nice sandwich, double side cooled, but the two heatsink, top one and bottom one, sit at the same temperature. Who was it telling you this?
no, it was only me actually. So I was investigating this one. So yeah, we didn't. I mean, like during simulation.
Devil is in details, right? It was so easy, fantastic, same temperature. I can parallel this network. No, you're not allowed. Different temperatures.
Okay.
In general, also in particular, when you stack up devices and whatever, how can you assume the top heatsink stays at the same temperature as, and even in a particular time instant, how can you assume it is forever? It is lasting forever. They have different stories. One heats up first faster than the other, cools down faster than the other. So this was a background assumption which is not necessarily correct in general. So I understand the outcomes of your study. However, it is not necessary as general as needed.
I understand.
All right. This was a conference. Yes.
Eurosim.
Yes, this was a Eurosim. Okay. Chapter 3, developing packaging. So the main difference between silicon, in my opinion, talking about packaging challenges, moving from silicon to silicon carbide, in my opinion, is power density. You can manage, you can handle the same current with basically the same voltage drop, with basically the same losses, with 1/4, 1/5 of the area. Silicon carbide chips are smaller than IGBT or whatever silicon equivalent devices. Power density is key point. You didn't mention once. You didn't mention a single time. That's the issue. Fortunately, silicon carbide has a lot higher thermal conductivity, but this nice story ends 100 micrometers below the surface.
Yeah.
So silicon carbide is fantastic, and then I have the same copper, the same solder, the same materials as before. So this is a key difference. And disappointingly, I didn't find any comment on this. Fortunately, it was in the chapter introduction, right? But you didn't follow up on this. This would be a key point. And this actually triggers a lot of discussion and a lot of probably speculation, so to say, on materials, on why the corner is worse than the center, because of power density, first of all.
Yeah.
Because the temperature swing in silicon would have been still acceptable, whereas in silicon carbide would be definitely not, because of power density. You missed a nice opportunity here. But nothing is wrong, just forgotten, just overlooked, you know? Vertical movement, I didn't like this. There is nothing really moving. Expansion, not movement.
No.
Right? No. So I think you got it, right? Chapter 4. Oh, yes, the heating power. This would have been interesting. I mean, I don't think you mentioned even once what your power was, what your power density was. Did you?
We mentioned volume averaged I mean, not in the thesis, but in the paper, I think we have mentioned.
Did?
Yeah, volume, like we have adjusted the volume averaged power losses.
Okay.
For getting the same temperatures.
It's watts per square centimeters or whatever?
I think it's
you said volume.
Meter. Yeah.
You said volume, right?
Yeah.
So per cubic millimeters or
cubic
cubic micrometers,
yeah.
whatever.
Yeah.
All right. I mean, the designer can easily work out what the power density is. But you know, one of the key parameters we have at packaging level is power density, again and again. So it would be lovely to have a number like, I simulated the 150 watts per square centimeter. Oh, that's good. I simulated 30. Okay, that's nothing, right? So just for you to know that that's a key parameter we are looking very, very much at when it comes to this. Yeah. Yes, nothing. Oh, by the way, AQG324 has now a new version. You know this, right? I'm the only one here who went through the references, probably. Really? 2025, version 4. All right? Chapter 5 is basically publication 6. I have no single comment there. Please correct me if I'm wrong. Chapter 6 is basically publication 7. Am I right here?
Yes.
This was my best finding.
Yes, yeah.
My best understanding here. So we skip this. Chapter 7. Now becomes a little bit interesting, I would say. Because I'm an experimental guy. I come from the soldering iron, you know? So be careful, be prepared. Well, number one, junction temperature is misleading. This is well and generally shared because, this picture is not taken from, this is probably the only picture I didn't take from your thesis. This is taken from Uwe Scheuermann, a life in Semicron talking about reliability and the packaging design. And this was a nice and impressive picture, which I afterwards reproduced when I was in Aalborg. So we shot at the chip during a heating phase and figured out how uneven temperature distribution is. It is astonishing. It is surprising. This was silicon, by the way. Silicon chip, I think it was, I don't remember sizes. I should have put it. I think this was 7 millimeters by 7. And then you have some 40 degrees different.
Yeah, it's quite different, yes.
From, the line was this one, right? From the corner to the center, right? And then when you go to silicon carbide, it can only be higher. I mean, it can be lower, it can be higher if you use the same chip dimensions. We are lucky, power density is higher, the chip is smaller, but still I expect we are in the range of this. This brings a huge negative effect at the packaging level. Sometimes I observed, already in silicon, by the way, delamination starting from the center. A bubble. SAEM analysis, scanning acoustic microscopy analysis, bringing a bubble in the center and nothing in the corners. Corners were perfectly safe and the bubble growing from the center because of that. If you overlook this effect, you might be tremendously wrong. I'm not saying you are. What I'm trying to say is that this should be not overlooked.
Yeah, I would like to comment here.
Oh, of course.
Yeah, so I mean, like we measured it using TSAP that provides the average temperature of the junction. And
yeah, go ahead, please.
Sorry, in our case, like for this device from SCT30 and 120, they have a single bond wire, which is kind of in the center of the die. And then what I feel then, like that bond wire might have expected higher temperature cycling than what we were actually measuring during the test because of the uneven distribution.
Right.
So,
Yes. Now, this is a little bit more, setup related. The setup is fine, except for one thing. I went through the waveforms here, and then what I figured out that you have an I total looking like the green one here, right? Which is apparently nice, but actually it's horrible. And you probably don't even suspect why. It is horrible for the current generator's sake. Your current generator is subject exactly to the same I total current, like this one. So your current generator is even more stressed than your device itself.
Okay.
You are killing your current generator. That's not the typical, I suspect it's not your fault, by the way, but that's another story. You probably used a ready-made setup in the lab or something.
No, actually we built it, and while building...
Then it's your fault. Sorry. It's only on you.
But this was like motivated.
Never, ever doing anything like this. You are killing your generator, which is probably 10,000 euros worth, or probably 5,000, depending on the current and voltage levels. Anyway, you don't do this. What you do is typically an interleaved structure where the generator is feeding two counter-switching layers or sides, where each of them is subject to on-off, but the generator is seeing a constant current. You are killing your generator like this. So this jumped immediately to my eyes. I cannot disclose you why, because my PhD student was great on this, but that's another story. No way. So, I mean, of course, your conclusions are sound because you actually power cycled your devices, but you also power cycled your generator. So it's not about your conclusion, it's about the health or remaining life of your generator, which is worth the publication itself. A little bit for kidding. That's also interesting. I liked very, very much. You talked about forward mode power cycling, inverse mode power cycling, and then I went to the kitchen and I told my wife, okay, let's make a mix-max of the two, right? How can I decide which one to go for and depending on what? Still a mystery. I cannot understand from you. I have some ideas myself, if you want. Then we can, when we take a coffee or eat together, I don't know, then we can discuss on this. But now I don't understand. You didn't elaborate. You didn't even mention this. So why should you use this one for what, and why should you use that one for what? Can you elaborate on this?
Yeah, so in the, I mean, according to the standard, it's the forward power cycling mode that we do. So we basically use the drain current to heat up the device. That comes from the standard. It also kind of implicates the real-time application where mostly the current flows through the drain. In the inverse mode, I mean, we also see the degradation related to the bond wires. I mean, inverse mode is easier to implement, so it's much more tempting than forward mode.
But why not using inverse mode only?
Because we wanted to go with the standard and we wanted to use the real test procedures that have already been followed.
Then why don't we just use the forward mode only?
So we used forward mode, but then we started with inverse mode because, as I mentioned, that it's much more tempting and it's much more easier because when we started with
Understood. Understood. I was suspecting something like that. The problem is that you cannot really match the one with the other. That's the problem.
That's the
right. So this makes your results a little bit more, I wouldn't say questionable, but difficult to understand because of this, right? But that's how it is. It's there. It's it's carved in stone. There is nothing else we can do for it. Failure analysis. Oh, by the way, I have a question. Did you perform failure analysis yourself?
No, we did it at. I didn't do it. We outsourced it.
Okay. Yes. Okay. This is true for both scanning acoustic microscopy and SEM.
Yes.
Okay. Yeah, it's fine. No problem. No one is supposed to be, owning every kind of instrument and facility. So fine. Red. This is quoting your statement. Red regions indicate the lamination. The only lamination I see here is between the plastic and and the lid frame. So this is not worth it all. I would rather zoom in. This is something you claim it's about the lamination, but my educated suspicion here is that this delamination is actually between the plastic and the chip. Look, it belongs to the same region, right? So you claim in your thesis that this is a principle of delamination between...
I would like to comment here.
Please.
We had a scanning electron microscope image for this also. I didn't put it in the thesis in the paper.
What is it? No results, only bond wires.
So from there we concluded that, I mean in the paper it is, I think.
Not sure. I cannot, I didn't go very much deep into the papers, the contents, but
I believe like it's one of the transaction papers. We showed like the solder layers has there's a small cracking there. But thesis I didn't put it.
I would have mentioned this more clearly and not relying on the first. I can imagine this is the best picture out of your 60, 70 samples. How many did you?
Yeah, I think not 60. We didn't sample all of them. It was costly. I mean, I think we degraded 80
No,
devices.
you power stack all of them.
80 devices. Yes,
How many?
Sorry. Around 80 devices.
80?
Yeah.
Impressive. But then, obviously, number 55 and number 19 were the best ones. I know. That's how it is. But again, your conclusion here, it's a little bit, sleepy, Nothing more on this. And that's fantastic, health diagnostics. So, health monitoring principle, yes, under power cycling. I would like to specify this, to highlight this under power cycling. Normally, I'm very strict on this. So to me, health monitoring is not under power cycling. To me, health monitoring is in real life, in real application. Elevator, escalator, motor drives, pumps, whatever, that's condition monitoring.
Yes.
Or health monitoring. In this case, it's laboratory monitoring, is instrumentation, is watching or whatever. Anyway, as such, it's still a good principle, it's still a good approach. You filtered, you proposed the two methods. One is moving average, the other one is SLR. RLS, sorry, which I'm not familiar with, so I learned something. Thank you for teaching me this, it's very interesting. You ended up in lift-off detection, right?
Yes.
You also cleaned up the natural linear slope, as you also elaborated during the presentation. So you managed to filter the lift-off only, which is great. However, you power cycle the DUT devices from Wolfspeed, am I right?
Yes.
There are 4 bond wires. However, I see 2 here, I see 3 here, I see 1 here.
So, can I comment?
Yeah.
Okay. In duty 1, if you look at the one region, then we suspect that the multiple bond wires have failed because we see that they are
simultaneously, same time.
Simultaneously, same time.
Okay.
And when we zoomed there, so we identified 3 peaks, but we haven't opened the package till now.
No.
So we are not sure. Also, it depends on when we stopped the test. The duty 3 is actually when we stopped it quite early.
This takes to my question. So probably there is something left. You stopped it earlier than the total failure, right?
In duty 3, we know we stopped it early because that was intentional.
Okay.
In duty 2, it can be that the threshold that we set stopped it before the entire device has failed.
Okay. Yeah. Regarding the amplitude, I didn't find much. Can you maybe elaborate a little bit more what the information in your amplitude is? I mean, this is a beautiful spike. I like it. But what is the information in obviously, the information in number of cycles is obvious. That sounds to me like life, available life. But the information in amplitude, is there anything we can exploit, we can use it for?
I mean, with this method, there will be peaks, so we can detect those peaks. And what we commented here is that the amplitude of the peaks actually reduces if we increase the forgetting factor in the RLS estimator.
But I mean, can you infer anything on the physical level? I mean, can you tell me? And it's a side bond wire, it's a central bond wire?
That we haven't investigated, but I think this makes a good study for the future work.
All right. And then I wrote it somewhere, how early is early, but I don't remember whether it is here or not. Anyway, I will ask you here. It's a key question for me. So you claim this is an early lift-off detection method.
Should be bond wire lift-off events.
How much early is early for you?
I mean, for us, it's like detecting early degradation of package. So before all the bond wires has lifted off and let's say the vehicle.
That's late. It's not early.
No, that's why we detect at the first bond wire level itself. So that's why I said early.
Understood. Yeah. So it is still functional. The first one is early for you.
Yeah.
Okay. Just for letting you know. People are working into nucleation of bond wires where the metal grains basically group together and get bigger and bigger.
Yes.
And detecting, well, I'm contradicting myself now with artificial intelligence, whoops, and detecting whether this is possibly causing a lift-off soon or a principle of cracking soon.
Yeah.
But that's when all of the bond wires are still intact. There is no crack. There is nothing like that. So I was really looking forward to learn how early it is early for you. But okay, it's the first, right?
Yeah.
So I would better call it first
bond wire
lift off instead of early, right? Yeah. Good. Looking at the chair, I think you allowed me to from 45 to 60 minutes. Am I correct? Lars?
You can go on. We are still finding.
So it's 45 minutes now. I think I have, well, 5 key and then conclusion. Okay. Yes. Chapter 7, publication 1. Nice review. I think it's a long paper. This is the energies one, right?
Yes.
Yes, this is the energies one. I loved it. It's very interesting. And I didn't have time to read it yet, but I will read it. It's very interesting, very nice introduction, comprehensive, 72 references. Wow. Not that common. Very nice. Even more than your dissertation, right? So good. Threshold voltage measurement, thermal impedance measurement. Excellent. Nice setup. By the way, finally, I saw the setup. You didn't put a single picture of your setup in your thesis. Come on. I understand you have it in the publication, but come on. You struggled to build it up for your own satisfaction or praise if you want. Just put it one. If not explaining piece by piece, right? You put a notional schematic, which was enough. I agree, but be proud. You know, you made it, right? So, not the first author. What happens here? You are claiming in your thesis a nice paper, by the way, where you are not the first author. Can you tell me a little bit the story behind?
Yeah, of course. So this research was done in collaboration with the scholar from China. And at that point, we were mostly focusing on building the power cycling test bench. And parallelly, I was also working on the simulation studies. So basically, we together start working on the power cycling bench and try to see like if we can implement the threshold voltage measurement, transient dual interface measurement for transient thermal characterization. So the paper is written by her, but the work and methodology and everything has been investigation by both of us. So that's why we decided that I will go as a second author and she can stay as a first author.
All right. All right. Fair enough. But I guess you know everything about this paper, right?
Yeah.
Can I assume you?
Yeah.
It's an important statement here because this is the only journal paper you have at the moment.
Yeah.
The other two are only submitted, unfortunately.
Yeah.
Not sure. At the time of the thesis, it was only submitted. I don't know whether you got any feedback from...
Yeah, we have.
One is transaction power electronics, another is open journal on power electronics.
Yes.
Did you get any feedback from either?
Yes, we have received. And I think...
what is that? Be honest.
Yeah, I mean...
Is the major revision is...
No, in the... it's a major revision, but...
Either or both?
So in OJPL, we have two acceptance with minor revision and one is reject or pass, right? So it's one.
Nice.
And we had people, I think we had 13 comments from all three
major
reviewers. So it's a major.
Okay.
Yeah.
Good. Good news. Okay. Congrats, by the way.
Thank you.
But this one was officially the only one at the time of writing. Conclusions are a bit inconclusive. Bond wires are more susceptible than solder layers. No comment. Depends on everything. Depends on PC mean, PC sec. Depends on sintering, soldering. Threshold voltage shift accurately measured indeed was not always consistent with on-state resistance shift. And you also admitted this in the conclusions, I remember. So you see here an increase in RDS on, but apparently for no reason the threshold voltage is decreasing, so they're not consistent. So, I mean, you are excused. By the way, this was an old paper. No, it was not this one. Sorry, there was another paper, 2022. This is a recent one. Okay, I mean, accepted recently, but then submitted, I don't know. But anyway, it was not this one. I understand, and it's still a valid paper. I'm not questioning it. So, but some issues there. Publication 2. This is basically, this was my comment here about being submitted late. I don't know whether this is a laziness or this is a...
No, it's because of the delays in the getting the data. Because 1 year to degrade all the devices.
I understand. This is typical, honestly, I have to say. So the final rush of the PhD. Is this a 3 years PhD here at KTH? Total 3 years? Yes. So in the end of the third year, in the middle of third year, oh, we have to publish. So I know. Fine, no problem. So not much to comment here. You explained in chapter 7. No, this was chapter 8. Yeah. Yeah. How early is early? We discussed this already, so I don't need to go any further into this. You used 5 seconds or 10 seconds for spiral cycling. This was a little bit questionable because you put yourself exactly in the middle of, fast and slow. Why? Just to make things more complicated or what? It was a strategic choice. I also copy-pasted the table here. Yeah, here it is.
But I think this will be fast power cycling because heating time is less than 5 seconds.
True.
And
you're right.
Yeah.
But why not using 2 seconds? Why not?
I mean, we were degrading multiple devices and we wanted to have different profile junction temperature.
Okay, I understand. Okay, so you use a 2, 3. Okay, I was this. Now I see the point. Sorry, I didn't quite catch at that time. So yes, you have 2, 3, and 5. Very good. Yes, fine. Oh yes. You did include a picture of the experimental setup. This was not my concern at this time, was for your reviewers' concern. I don't know whether you got a comment on this.
We didn't.
Lucky you. But normally, if you don't have a setup,
I would have included it.
Yeah, that would be a good idea. Already discussed for chapter 7, so we skip this one, publication 4. This was SIPS 2022. This one was probably your first one.
First paper, yes.
Yes. This is the mother of publication 2. It was publication 8, right?
Publication 8, yeah.
Yeah. This is now taking me to minor comments. So we went through all the chapters except for the conclusions. PDF links do not work. I love PDF. I mean, I will save your hard copy in my shelf, but I use the PDF and then click like references, click, nothing happening. So for some reason.
But I think I ensured that they were working. I don't know what's the problem here. So
try.
I will double check, yeah.
All right, just for your knowledge. Base plate attach, die attach. It took 5 minutes to me to figure out what it is. I understand. By the way, I hate acronyms. Acronyms are there for no reason, only for for laziness. The reader is only puzzled all the time with acronyms. What the hell is this meaning now? Oh my gosh! Stopping. You are in the middle of I understand. What is this? And then you have to stop. You have to jump. Why? Because you are lazy, not writing base plate attach or die attach, right? So I understand overusing the same wording is annoying. I understand, but sometimes just beginning with BA, DA, DA, BA, something like this. I had to struggle again to understand what SCT19 was, and then I realized it was a DUT from ST Microelectronics. It took 10 minutes. SCT, what is SCT? Is an acronym, is a DUT, SCT. No, it's just a duty from ST Microelectronics. Come on. I mean, this is a very, minor thing. So I put everything on this slide. Yes. You can redefine acronyms every time, at every chapter, every section if you want. No one will kill you. It's all the way around. If you only define the acronym in chapter 1, I have to jump from chapter 8 to chapter 1 all the times and find out where in the text the acronym is. Right? So,
I understand.
Acronyms, right? Yes, that was long. Final checks. Did the PhD answer the research questions? Is anything missing from the expectations? And this takes me to chapter 9. So you claim comprehensive investigation of package level reliability issue in silicon carbide MOSFETs. You claim your thesis is basically made up of 2 parts. Yes. The first one regarding analysis, the second one regarding experiments. I would say they are a little bit imbalanced. So the part one is obviously bigger than the second. I'm not saying the second is not sound, not at all. I'm just saying you spent more time on part one. That's how it is. No comments here, no questions. This is what I figured out from your conclusions, and actually they sound, all of them, to me perfectly reasonable. So I agree with your conclusions, which probably is a major statement.
Thank you.
Future work you propose, well, everyone is asked to write the future work, but everyone doesn't care a bit about the future work. It's other people's business, it's not my business. So I will write it down, but I don't care more than that. Anyway, just to credit you, let's go through the future work. Experimental validating the proposed lifetime model. Yes, please. Yes, please. I agree. New spacer interconnection material. Yes, please. You don't just use molybdenum. You can use other compounds and other things. I agree. And I won't comment on this because what you did is has actually nothing to do with real life. You cannot use inverse measurement, diode measurement in real life because you don't have time. You're switching. You don't have blank times where you can feed a measurement current. So simply no comment. Wonderful to state, but you have to start over. You have to think differently. You have to. So fair enough. You put in the future work. I liked you didn't put in the conclusion. You didn't say I did something for real life. I would have killed you, because that's not true. Future work, it's fine. You can put whatever you like, right? No problem. Purpose. To investigate the thermomechanical performance, to understand their failure mechanisms, to examine advanced packaging materials, to improve performance, to design a robust power cycling setup, to use power robust. Well, we commented already on the current generator's health right here. All right. But other than that, yes, it's robust. To use power cycling data for development of reliable health diagnostic methods. And I would say check. Right? Expectations. Back to slide number 7. So, thermomechanical reliability analysis of silicon carbide MOSFET packaging. Come on. The whole chapter 2 was on this, plus publications. Top side interconnection. Yes, you did it. By the way, I didn't see a single time copper bond wires on aluminum. I think you break it. You break the chip. So you made simulations, fine, but it's kind of pointless because it's fine. It's one extra thing you did. I'm just saying it's pointless because you break it. And that's why Danfoss came up with DBB, because copper is actually, among other benefits on thermal point of view and so on, it's also spreading the soldering, the bonding force. When at the bonding time. So just for your knowledge. But yes, bottom side interconnection, yes. Sinter, solder, yes. By the way, another comment here, you use only silver sintering.
Only silver.
Copper sintering is becoming very popular because it's a lot cheaper than silver.
Yes, now at least.
Yes, but when you started, probably
silver was not this expensive.
Health diagnostics, you did. Detection method, you did. Early, we can talk later, but it is a detection method, so check. Conclusions, without spoiler. I cannot tell you my opinion. This is secret. I will share with the committee later on, and then they will tell you in the end. How can we summarize your work? Well, a compound of 4 ingredients: thermomechanical finite-element simulations, analytical prediction of time to failure, component life, power cycling, and data processing. Even percentages? No. Finite elements, thermomechanical. I put the TM on purpose because the E is missing there.
Yes.
Was I would say the biggest part, or together with data processing, you struggle with the 2 methods, right? Analytical prediction, lesser, and experiment, even lesser. So yes, it's a combination of 4, not even distributed, evenly distributed, I would say. And with this, I conclude my opposition.
Thank you very much.
Thank you.
Thank you so much, Professor Iannuzzo, for a very interesting discussion, and thank you too to Bhanu. Next, we will be moving over to questions from the grading committee. And we will be starting in order of having traveled the furthest, which puts Dr. Ivana Kovacevic-Badstubner in pole position. So please, you can use my microphone here. And you're welcome to stand here as well if you... I guess if you come up here, people see you online. That's even better.
Okay, thank you very much for your nice presentation.
Thank you.
And I will go back to your to the paper and lifetime modeling. So, and you compare lifetime in power cycling lifetime of discrete.
Yeah, discrete devices.
Yes.
Oh, sorry. Yeah, there.
Okay, so you have comparing a power cycling lifetime with some lifetime model from the literature.
Yes, that's from the references.
Yes, and this is for modules.
Yes.
So how would you comment the difference now between modules and discretes?
There is a fabrication difference. I mean, modules have a DBC and discretes don't have the DBC. I mean, we didn't compare exactly because we didn't have sufficient data at that time. So, but we mentioned about, as Francesco mentioned, this is also kind of a review paper that there are different lifetime models. And with that figure, we wanted to highlight that the solder layer and aluminum lifetime can vary depending on the mean and the delta T profile. So that's like the our proposal there. So we are not actually comparing the two, but yeah, as you are right, that I mean, in discrete devices, it can be different. I mean, probably we can have a more bond wire related failures than power modules.
So for me, it was missing, like you also stated at the beginning of your presentation, elements in the package, but one thing was missing, and it's encapsulation. So the difference between encapsulation of discrete and standard encapsulation in module could also affect reliability of bond wires.
Yes, epoxy is a bit tough, and there is also a study in the past where they have basically compared different kind of encapsulations. Epoxy is tough and it holds the wire at its place, and it can have more impact on, I think, on the bond wire reliability when you compare with the gel, because gel is much softer, so the bond wire can freely move here and there. So for sure, it has impact on the reliability, but for simplicity and making our model simple, we didn't include it. We, however, involved encapsulation, I think, in double-sided cooled packages. Yeah, but not in the single-sided at least.
And then you would comment then a failure like a lift-off and heel crack. Because you also write in the thesis that heel crack is affected by silicon carbide. So for example, would you distinguish a heel crack as a failure mode with silicon chip and silicon carbide chip?
It's mostly related to aspect ratio, I think. So if the aspect ratio is high, which is basically height divided by width, then we don't get heel cracks. It's mostly the lift off. But then if the aspect ratio is lower, then it's the lift off. It's the heel crack, which we can also observe. And I think this study has mostly been done on the silicon packages. Yeah, but I think like heel cracking is mostly relevant with the aspect ratio.
I would add there also encapsulation plays a role.
Encapsulation definitely, because it will hold it, and then I mean, heel crack happens because of ohmic heating, and the wire expands, contract, expand, contract, and encapsulation will hold it, will kind of have an impact on the failure mechanisms that are happening inside the bond wire. So definitely it have an impact.
Okay, and what would you did a lot of power cycling, so that's really nice. So what was your challenge to develop a lifetime model?
I mean, we wanted to proceed forward with the advanced packages because this discrete packages has already been studied a lot. For us, the biggest challenge was not developing the power cycling, but the fabricating the package itself. And we tried a lot. I bought the semiconductors, studied the metallization. For example, for double-sided cooled, we should not have aluminum metallization on top. At that time, there was a semiconductor crash. I got the first chip after 1 year of ordering from Cree. So we did multiple consultation. But in the end, it was not feasible enough for us because it required a big competency, which I feel like in KTH we don't do fabrication that much, so we don't have it. So that was the challenge. I mean.
But for example, for discrete, commercial discretes, that's what I was more targeting. So you did a lot of power cycling on commercial discretes. And then would you be able to put them in this lifetime curve? I mean, you did quite some samples cycle.
Yes.
What would be the challenge? So not related to this new advanced package.
I understand. So there are two aspects on this. One is if we want to use physics-based model or we want to use the analytical models. I actually tried to use physics-based model, and I was parallelly working on this. I couldn't finish before finishing my PhD. So I have a COMSOL model of this device. I investigated the type of solder materials that they use. And also we were trying to do the thermal characterization, but we were parallelly also doing the power cycling. But we would have tried to validate the physics-based lifetime model at least. But I mean, like this thing we started, I mean, maybe in 2025, mid of 2025. So we couldn't like finish everything. Okay. But that I would have loved to take it forward and like make the lifetime model.
Future step.
Yeah.
And one more question, so and then viscoplasticity. And you are then like a bit term in your thesis is time dependent and time independent. So I think in viscoplasticity, it's typically what you said, it's time dependent behavior.
I said both,
I think.
think.
Common, but it is time dependent.
Time dependent, yes. Okay.
So, and then you say also, I think, Francesco, you had on the comment on the slide that it's a dominant, or it should be included for silicon carbide or either silicon steel. But what do you think when this viscoplasticity becomes dominant?
Because at high temperature, because of creep, when the temperature goes above homologous temperature, which is 1/3 of the melting point of the material. So if solder layer had lower melting point, like 220 degrees centigrade, so at high temperature, the creep comes, and then if the cycling is slow, then I mean this plasticity will happen because of the cycling, right? But if the temperature is kind of steady at high temperature, then the time dependent creeps comes into the play, and then I think it will become dominant.
So both time scale and the temperature.
Yeah.
So that just could be precise. Yeah.
Thank you.
Okay. So that would be all from my side.
Thank you.
Okay.
Thank you very much. So next, Professor Jacek Rabkowski, please, and step into the screen, please.
Yes, thank you. The image is most important today. No matter what we say, we should look nice, right? Just joking. So thank you for really good work and nice thesis and great presentation. I'm really impressed how many things that you've done and quite a high number of publication, I would say. But the drawback for me from the thesis and also from this presentation is that you're trying to avoid the definite conclusions, right? Just two examples. I will try to ask you for this. So you was doing this simulation of double-sided cooling with different spacers. And I was trying to find the conclusion, which ratio of copper and molybdenum would you recommend? Can you answer this or?
I mean, like there are 3 solder layers and we get different viscoplastic dissipation density in those 3 layers. From the paper, from this, it looks like it's the die-attached solder layer, which will fail the first, and molybdenum is the worst because in that it's highest. But I didn't want to just say without experimental validation because I didn't have it. And also, I mean, yeah, it's mostly because of the experimental validation. And plus, we don't know exactly, like, I mean, it's good if we validate it by testing that as that layer that will fail. Otherwise, I feel like it's the die-attached solder DA bottom that is underneath the die that will fail because of high viscoplastic dissipation density, and also in case of molybdenum where it's the highest, then it will molybdenum is worse.
Okay, so it's still too early to say something.
I will say that one. Yeah.
Okay. Okay. I see. Then also a little bit going back to the discussion that was started by Francesco, that you had these two types of setups, inverse mode and a forward mode. So let's imagine that I'm starting in the field and you spend quite a lot of time on this. Which one you recommend?
I'll go with the forward mode because that kind of mimics the real application. Inverse mode, as I mentioned earlier, is like easier to control and develop, and that's why we started with inverse mode, because this was the first time we were starting in the power cycling, and then eventually we proceeded to forward mode. But I will go with the forward mode power cycling.
For the forward, but it doesn't require like much more current when you go.
I think current-wise is fine, but then we need gate drivers to switch on and off because we can measure the junction temperature with we can use TSEP. I will not say measure junction now, but we can use TSEP for the temperature measurement in cooling mode. And then for that we have to turn off the device. And plus the failure mechanisms are different in inverse and forward mode. In forward mode, the high current does not flow through the bond wire, it flows through the drain channel. So we see the real challenge, like real degradations that we see, like for example, threshold voltage related drift and all these.
Yes.
But we will not see them if we do inverse mode, because inverse mode degradation will be more related to body diode rather than the channel.
Yeah. Yeah. So you already answered my another question. But what if we would combine those two? If we will switch on the channel in the inverse mode, would be possible?
If you switch on the channel in the inverse mode, like by just keeping the gate voltage 0, then the signal will be impacted by the threshold voltage drift, and because the channel is also included in the current conduction path. And this, I think, is also being used in one of the publications in UIC, I think, where they have shown that we can use the body diode voltage drop by different gate voltages for detecting package-related failures. Yeah.
So, the answer is still not that clear, right?
I mean, we can use it. If you open the channel, then the body diode voltage will also be drifted because of the threshold voltage drift.
Yeah,
I would like to say that.
Yeah. But the most important is that using the body diode only, you are not touching the channel. And that's. But one more comment or question to this inverse mode, because you was measuring the temperature at first at the end of the heating phase, right? So using 10 amp current, and then the second measurement was at the end of the cooling phase with 10 or 100 milliamps. So why you didn't wait for the current to disappear, and why did you didn't make the first measurement with this small current?
I mean, it was a bit easier to make it before the switching. So that's why we did it one at the maximum and the other at the minimum. And also in order to maintain the same temperature, we did it this way.
Okay. So I see. So that's a very good explanation. I'm also quite curious because you picked these values of the currents that you pulsed, the devices like 10 amps, 20 amps. That was just a reason to select this value in reference to nominal current of the device, or
in forward power cycling.
Yep.
It was. I mean, we wanted to achieve the delta T and TG mean. So we didn't focus much on the current, but on the temperature. And then we also wanted to adjust the gate voltages. So for one particular gate voltage, and we want to, let's say we want to achieve 1 delta T. So we adjust the current based on that. So for example, like I didn't mention in the thesis, but we cycled 80 devices and we tested at, let's say, a series of current, like 32 amps, 33 amps, 34 amps, and like this. But there was no strategy behind selecting the currents, I will say. We were mostly focusing on the temperature cycling.
Okay, but there were some calculation and what you expect. It was not like you said, okay, I will just apply 10 amps because this is nice number, right?
No, yeah, of course.
Okay,
yeah,
okay.
we wanted to go with the temperature cycling.
Okay, and maybe the final comment. So for your future works, taking into account that this RDS-on is really affected by so many factors. So do you see in the real life this health monitoring like real or extremely difficult or possible? How do you comment on this?
Yeah, I mean, like in the real inverters, that's something which needs to be investigated. One challenge I think is like it cannot. I mean, we can do it during maybe on and off situation. I mean, when let's say we have a vehicle and it is stopped, then maybe because I mean, the main thing here is we want to measure the junction temperature, and if there are ways which we can measure the junction temperature online, then probably it needs to be investigated. But we are using the body diode voltage as a junction temperature sensitive electrical parameter. So for that, we need to have a converter in off state so that we can inject this current. So I will say it's a bit challenging, but that's how I put it as a future work. And also, as Ivana mentioned, that we have modules and then we have discrete devices. So this is done in the discrete devices, but in powertrains, we have mostly the modules. And in that, we have multi-parallel chips. So it needs to be investigated how this algorithm can be used in the multi-chip power modules as well, if it's feasible enough or not.
Okay, so I see that it will be difficult and challenging, but possible, right?
It should be possible, I will say. Yeah, but I cannot comment like if it's like it can be done, but it should be possible.
No, that's why you put this in future work.
Yeah.
Right? Okay, so thank you so much.
Yeah, thank you.
Thank you very much, Professor Rabkowski. And now, last but not least, Thorbjörn.
Thank you. So first, I would like to say I think you have done a very nice and interesting work and in a very timely subject. And also, I liked one of the things I liked a lot was this temperature compensation algorithm for predicting the bond wire liftoffs. And then I want to continue that with that. When you showed, for instance, I can't remember which one it was, but where it indicated a rather big spread before failure for the different samples you tested. In one figure, it was three MOSFETs.
Yeah, I can come. I can
maybe you have that
put
figure.
The presentation. Yes, sorry. And then maybe I should go with the. So this is with two MOSFETs, and then this one?
No, before, I think.
Okay. Here?
Even earlier.
Okay.
Maybe not so important, but I heard Francesco ask you about number of samples. I didn't really hear. Did you say 80 samples that you tried?
In total, we degraded around 80 samples.
80 samples,
yeah.
Okay. And those you didn't take into the thesis, what happened with them?
We have the data, and maybe the future. We have the data with us, so maybe the future student.
Since those you presented seemed to have a big spread, then I was a bit curious if it was, since you had so many samples, did the tests go okay, or did you have malfunctions of other reasons? Or
No. So all the devices that we degraded, I mean, they were tested. They failed because of the reasons we were foreseeing already.
Okay.
So the test has worked properly, I will say. Yeah.
Okay.
And also we also see that we get reduced number of cycles to failure if we increase delta T. So we also looked into that aspect as well. So I mean, I think like everything went well.
Okay. Then I was also thinking about the thermal grease or thin layer there for when you attached it to the heat sink. I guess these tests, when they are quick, are far too quick for any problems on that on the thermal grease, or?
So what we used in our case was the gap pad. It's soft, and so it pumps out during power cycling. So we see pumping out in all of them. So
you did? Okay.
Yeah, we see, and that's why I would like to show here. I didn't mention, but you see the decrease in the maximum junction temperature in the beginning. That's because of the pumping out effect of the gap pad material.
Aha! I thought it was of the reduction of the channel resistance due to change in threshold voltage.
No, this temperature is also reducing, and this was because the cap pad was thicker in the beginning, and during the power cycling, it pumped out, and then it became thinner and thinner.
Okay, you have an interesting picture in Article 1, where you have the thermal impedance shown for different cycles. It's paper 1, figure 17, I think. Where you could see that you have the time on logarithmic scale, and then you see that even for the last power cycle you couldn't see any difference in thermal impedance.
No.
And then I was a little bit surprised that okay, as you say, if you see a pumping effect already during your test.
But we had a different I mean, those devices were tested 3 years back. And the power cycling that we did with multiple devices started last year. So we had a different thermal interface in that case. I will not like to link these studies together. I would say these are separate studies. Yeah.
I know a long time ago it was also very important in wind turbines, if you put them horizontal or vertical, that you had a serious pumping effect if they were mounted horizontal. So which direction did you use?
Let me figure. Think. So it was vertical.
Okay.
Yeah, because we had a cool.
Then okay, somewhere you mentioned about that you focused on the power cycling method, but somewhere you write among these methods you use the power cycling. Which other methods would be useful for in your work? It's on page 49. I was just thinking, which methods do you use otherwise?
Actually, there are 2 aspects. Just let me double check. In Thesis on page 49. Yes, so accelerated lifetime test, it can be a thermal cycling test, for example, inside the climate chamber, which is a slow power, which is a slow accelerated lifetime test. So what we focused is the power cycling test, which is an active.
I think thermal chambers will be very slow.
Yeah.
But maybe you can have a liquid in a heat sink or something.
Possibly, like
quicker.
Yeah.
Then I also, like Jacek, I was also thinking about that you could be a bit braver when you have done some analysis, we see some results, and then I was always thinking, so what is your recommendation? So if you looked upon the different solder types, is it worth with a silver sintering, or is it not worth?
Yeah, silver sintering is, I think, is better, and that's why in the presentation I concluded that part. Yeah.
I've now heard about copper sintering.
Yeah. So copper we haven't investigated. Yeah.
Okay, so I was also thinking, you can dare to be a bit brave.
I understand your point.
And then did I have a final comment? It was it was just about where you had you had the slide where you compared the asymmetric, and the full model, and you predicted where you would have delaminations. Have you seen anything in literature or anywhere else that that goes hand in hand with your findings?
So depending on the position,
Yes.
asymmetric. No, I think we didn't find literature which have basically focused on optimizing, or which are focused on failure mechanism, depending on the geometry. But there are, I think, probably optimization studies that are done, for example, to see like how the dies should be placed in order to provide the best thermal performances. But coming to the lifetime side, I think I have not seen many studies, or I have not seen papers where they have actually done the test.
I understand that it could be difficult to find. Then I had one final. I was also curious when you had this formula, and we had this plot that was measured, where you had the RDS as function of gate source voltage, and you had the equations also. Did you try to check the values in the equation towards the measurements, or didn't you have any data at all that could be used in your theory expressions?
Can you please explain which?
Yes, it was you had the one plot where you had RDS as function of gate source voltage.
Okay, then maybe I should go to the thesis. This one? No, this is.
No, it was one where you summarized, I think, the channel resistance and the drift region resistance.
But I understand it's not in the thesis, that figure, it's in the paper actually.
Yeah, maybe it was.
Yeah, and it shows the negative temperature coefficient and positive temperature coefficient, which Francesco showed, I think. Francisco's presentation, I mean.
Yeah. Okay. But Francesco actually had this very similar question. And I was just curious if you tried to do some calculations, or you didn't do it at all.
We didn't do it. I mean, we were more interested in seeing if it is showing the negative temperature coefficient or the positive temperature coefficient, and when at what voltage level this transition happens. But we didn't validate the equation with the experimental part.
Okay. Well, thank you very much. With this, I leave the word back to the chairman.
Thanks very much, Thorbjörn. Well, thanks again to the grading committee for extending the discussion. Really good questions that we have examined the work from many directions. And finally now, if there are any further questions from the audience here in the room, do you see if there's anything, or do you, Staffan, if anyone online wants to say anything? But please, anyone? Please.
I'm not sure I dare to put a question after this extensive opposition and defense and complementary evaluation. But just for the fun of it and the future work that I think Francesco doesn't like, but are you planning to start a company on your work or not?
No.
And why not?
I mean, like, this can be something which can be taken forward by the future students who come to KTH. So it's also like maybe we have more projects here, and then the future they can validate it with multi-chip power modules and all. But right now I am a guy who lives on resident permit, so, and I have a job now. It's nice, so I will.
All right, thank you.
I'll continue with my job.
Okay. Anything online, Staffan? No, okay. So I will allow 20 seconds of awkward silence to make sure that there's really no questions. That was awkward, but now we can be certain that there is really no questions. So I suggest we thank Bhanu and grading committee and opponent with a big applause. And with that, the open part of the defense is closed. The grading committee and opponent will now convene for a discussion. And I don't know, Bhanu, do you have any instructions for the rest of the audience?
Yeah, so people who are here, maybe my colleagues can direct you to the kitchen, and I think we all will gather in the kitchen there in Technical in 33. Yes.
Great. And for those of you online, thanks for attending, and have a nice weekend.
Thank you.